Surface temperature, there are very different surface temperatures. We have on Wednesday a lecture by Claire, who will also let you know something about the different surface temperature products. And what I will cover in this lecture is first, what does the thermal camera see actually? What are the components of the signal recorded in the thermal camera? This is something that John already touched upon, which will lead to the radiative transfer equations and different models. And from there, we will go to different algorithms for surface temperature retrieval. And I will try to make you aware how are they different, what are the different assumptions between those algorithms, and how are the results of these algorithms different as well, as in what are they sensitive towards, what are the biases and accuracies to expect. So this is something that you probably are familiar with. So this is the same type of camera that you can have in your phone. You can easily distinguish objects. This is actually where we are now. That's spacebar. And so this is when you are given such an image, you will distinguish it right away. What is what is vegetation, what is water, and this is the type of a spatial resolution which we can see in things like Google Maps, Google Earth, or Apple, whatever sources are there. Then the first difference to the thermal camera is the resolution. So here you will see the grid created with the magenta lines here is the spatial resolution of a currently one of the highest available in terms of resolution, ecostress. So this is 70 by 70 meters. And therefore, what you see inside of such a pixel here, this is going to be one number, one color of a grayscale. You'll have a mixture of grass, building. Here you'll have some other areas. You'll have some very sealed areas like the parking lot where some of you might have left your car this morning. And all of that will be a single number for each of those pixels. So what I would like you to remember is what is a reflectance in the visible or near infrared spectral range it's not going to be a reflectance in the thermal, but we still have the very massive problem of a mixed pixel. And so let's go and look at a different aspect. So we already know we don't see reflectance. You'll see radiated heat, and you'll have also emission. So the components of the thermal signal at the surface is emissivity, what John already mentions, as well as temperature. So this is our radiation at the surface. Then again, we go through the atmosphere. So all the effects that Mike previously mentioned will be then strongly influencing our signal going from the surface to the satellite. And so when we go through the atmosphere, we then have a heat from the area, mixed pixel from all the different surfaces going upwards through the atmosphere. It's going to be changed. Then we have something similar to a Planck curve, but it's not going to be a Planck curve. It's going to be also changed by the emissivity in a specific spectral range. So to take that a little bit deeper, what does a thermal sensor see? We have first the surface radiation. So that's what we're mainly interested in, or at least that's what I'm interested in my research. Then we have also the atmospheric radiation. So something that the temperature of the atmosphere, as John mentioned, it will be another component in what the sensor records. Then we have reflected atmospheric radiation. What it means, atmosphere radiates, the radiation of the atmosphere is reflected from the ground, goes back up to the sensor. This is the third component. Then we have another component. If we have one surface, the radiation can come from that surface, be reflected from another surface, then go through the atmosphere. So we can make it very, very complex. We can start to go here, then reflect here, then re-reflect, and then go up. We can make that type of equation very, very complex. Some of those components are less relevant because every time the signal crosses the atmosphere, the overall amount of radiation will be smaller. And so some of the components here are less relevant. So we tend to forget some of them, or we accept to not account for them because they can be just too complex to account for in the first place if we don't have information about the digital elevation model. So what we want to remember, 3 very important components: surface radiation, atmospheric radiation, and reflected atmospheric radiation, sometimes also called the downwelling. Then we also want to understand how the characteristics of those components. If we start with the temperature is highly dynamic. So the temperature will change throughout the day and night, obviously. It will depend on season, on the weather, on events. Surface temperature will again change if the surface is wet because it's rained. So this is very, very highly dynamic. But temperature is sensor and wavelength independent. So this is something to remember. Then the emissivity at the same time, it is dynamic, because if, again, the surface is wet, then the emissivity will change. However, it is less dynamic. So if we have a dry surface and we image that same surface throughout many days, and the land cover didn't change, we can expect more or less the same emissivity. It is weakly dynamic because if we have plants, the plants can actually change. They can become stressed, and so emissivity will change. But the dynamic is not as strong as in temperature. Then again, emissivity is wavelength dependent. It's a spectrum. Now, the atmosphere is the most complex because it's highly dynamic. It can change within minutes. But it's also wavelength dependent, as we know already from Mike's lecture. And so however, what we need to remember about the atmosphere, and especially from Adam's lecture, we have different sources of information, different bands from maybe visible range or 1.38 channel, which will give us additional information. Okay, so I hope you know what Kirchhoff's radiation law is. What that law will tell you is that there are 3 components of interaction between light and a surface. First being absorption or emission, reflection, the second one, and transmission. So if we assume that the Kirchhoff's law tells us that transmission, absorption, and reflection together equals 1. The ratios of them together are 1. So if we consider materials which aren't transparent, and we mean in thermal ranges, in this case, we have a situation where absorption or emission is equal 1 minus reflection. So on the plot on the right, you have a spectrum of aluminum in the wavelengths of between visible and thermal. And the higher the emissivity, the lower the reflectance. This is quite intuitive if you think about aluminum, because aluminum is very bright. It can be also used to produce a mirror. So if you think about what you see a very bright material, but the reflectance of the same material in the thermal range will be much, much lower, will be much higher, and the emissivity will be much, much lower. This is very important if you plan your aerial survey and you want to have sort of low-cost components. You can use such materials if you know their emissivity. I think Jennifer will tell you more about that tomorrow. So this is emission versus reflection. Another part is what we already mentioned. Emission is a spectrum. So here on the left, you see again the same plot of aluminum, which is quite clear because the emission is very high in the visible wavelengths, and it decreases throughout the spectrum with the wavelengths. Whereas grass on the left, it has a complicated spectrum. It has features. It goes up, down, and so on. And this means that you can actually use emissivity to identify surfaces, as you do with your spectrum in the visible wavelengths. Some of those features are unique for thermal spectrum. So therefore, you can actually identify some of the minerals using emissivity spectrum. And I'm absolutely sure that Simon Hook will tell you something about that on Wednesday. But this is just to let you know, emissivity is a spectrum. So it's not just a factor that you multiply on your Planck function. So now I've let you know about all the difficulties. We actually have more unknowns than measurements, because we have, in each band, we have both temperature and emissivity, and there's just one number, one measurement. And measurements in the thermal wavelengths are highly correlated. What it means is we have one temperature throughout all the bands. And if you look at the grass spectrum here, the range is all above 90% here in the thermal range, which means that the measurements will not be strongly different to each other. So therefore, we speak about highly correlated measurements in the thermal wavelength. But not everything is so bad. So the more measurements, the less uncertainty, because again, the temperature is the same for all the bands. So basically, we need more bands. Then also, the more is known about the state, the better. So if we know something about what to expect, we can narrow down what we are looking for. For instance, we can take the atmospheric parameters from other sources. We can add visible bands to our thermal bands. We can take the state of the atmosphere from different measurements. We have, for instance, things like ERA 5, which gives us hourly parameters of the atmosphere. And then, last but not least, understanding of the spectrum. We need to understand what we're expecting to see. And therefore, there are things that will enable us to make accurate algorithms. For instance, there is a similarity between the measurements in bands of 11 and 12 microns, which are basis of the so-called split window algorithms, which I'll let you know in a second. So the more we know, how does the spectrum look like, what to expect, the better we can account for all these uncertainties. So now we understand the components a little bit better, we can go to the radiative transfer. So we've seen that in John's lecture. This is a little bit of a simplified version of that. We have radiation at the sensor, which consists of three components: radiation of the ground, radiation of the atmosphere, and radiation of the atmosphere which is reflected from the ground and goes back up. So we can simplify that. We can treat that as simple, but obviously the uncertainty will be higher. We can go a little bit more complex. And to break this equation a little bit more down, we have, for instance, this part which accounts for the reflected atmospheric radiation. So you see here 1 minus epsilon. This means that this is the reflected part. So this is first one. The other component, surface emissivity. And here we have the black body radiation of the temperature at the surface. So all of these components, then we have also the transmissivity of the atmosphere. All of these components can be taken into account in this example radiative transfer equation. We can make things even more complicated. And I don't expect you to remember all of those equations. Here we can break down this a little bit more complex equation, which I took from this publication, which you can break down the elements into surface emission, surface reflected downwelling atmospheric emission, which we already spoke about. Then we have another component, which is scattering. As John mentioned, is less relevant, but we can still account for it. And then something that we haven't mentioned yet at all is the surface reflected solar beam, because there will be some minute part of solar energy reflected as well. So we can make things, as we did with the graph where the arrows kept appearing and disappearing, we can do the same with the rotative transfer equations. And now that we know that, we can go into the groups of algorithms for retrieving LST. The first group are the mono-window algorithms. These have been used heavily in the very beginning when we didn't have much data. We have, for instance, for some Landsat sensors, we only have one thermal band. That basically means we only have one measurement for all these unknowns. Now, the second group, which I called here algorithms assuming emissivity, the mono-window algorithm also assumes emissivity, but I still wanted to split those two. The second group are the split window algorithms that use the information that the emissivity in the window of 11 and 12 microns is very similar. Now, the third group of algorithms, which is emerging strongly now, is the algorithms retrieving emissivity as well as temperature. So among these, we have NASA's flagship algorithm TESS, temperature emissivity separation, which is operation for everything that you download from NASA, so EcoStress, MODIS, views. Then we have direct TESS algorithm, which is not used a lot yet, but it will be operational for the future mission Trishna. And we will have Philippe Gamet, who will tell you more about Trishna. And then lastly, we have optimal estimation, which will be operational for the future mission LSTM. So let's start with the mono-window algorithms. So as I mentioned, emissivity is assumed. And it also requires some external additional knowledge on the atmospheric profile. So what these algorithms do is basically assume all these parameters that I marked here with the red boxes. And then we have actually one measurement, one unknown. So, okay, the uncertainty of that will be quite high. But this is the first thing you can do if you have only one measurement. If we go to split window algorithms, they base on the high similarity of emissivity within two neighboring bands. So you'll have two bands within the red box marked here on that spectrum. The emissivity is similar. It will never be exactly the same, but it can be assumed to be the same or very, very similar. So basically, if we have good knowledge of the atmosphere from external sources, we have two measurements, but also two unknowns, the temperature and the emissivity. So that makes the math a little bit easier for us. And what these algorithms typically do is they use coefficients to parameterize emissivity of the surface. First, we can start with the algorithm, University of Leicester algorithm, which is actually operational for any Copernicus LST from Sentinel-3. So if you see any Copernicus data sets of LST, that's the algorithm. What it does, it takes Nadir retrievals from two bands, and it has coefficients which are dependent on various parameters, being surface or vegetation type, which we account for as biome. This is based on land cover CCI biome. So if you want to find more information on that, you can. It's well documented. It contains information on vegetation fraction, which is seasonally dependent, as well as precipitable water, which is then also seasonally dependent, and then all of that on viewing angle. So we have NADI retrievals, but we also account for the angle deviation from that. So basically what it does is it took a huge number of simulations. It trained the coefficient values to create lookup tables for all the possible cases. And therefore, it's very fast because it then just reads the values for the coefficients. The next algorithm, a similar one, is generalized split window, which is operationally implemented for Modus and Severi, and a lot of LSTCCI products altogether. So if you're interested in that, you can find more about that in the LSTCCI workshop, where you have, again, 11 and 12 micron measurements, top of atmosphere, brightness, temperature. It's the same case for the UOL. What Mike mentioned, sometimes the algorithms will take bottom of atmosphere, these take top of atmosphere, and the coefficients include already information about the atmospheric parameters. This one takes mean land surface emissivity, but it somehow accounts for the difference expected. And you have actually 7 different coefficients here. So basically A1, A2, A3, B1, B2, B3, and C. So these were our split window algorithms. And now we go to the group that retrieves both emissivity as well as temperature. So the first is NASA's flagship algorithm, TESS. It does retrieve both temperature and emissivity. It bases on the assumption that there is a physical relationship between lab measured spectrum and the spectral contrast, which I will show you in a second, a plot on that. What it does, however, it requires already atmospherically corrected data. So you have to have an atmospheric correction module before you do anything with TESS. So input is then bottom of atmosphere radiance. Then TESS is an iterative process which bases on a few sensor-dependent thresholds, which is nice because then it accounts for the noise within the sensor, NEDT. And as I mentioned, it's operational for NASA's products. So TESS consists of 3 modules. They're called NEM, RAT, and MMD. I don't remember the names for that completely. Maybe I'll remember later in the lecture. The NEM module is an iterative process of refining the parameters from radiative transfer equation. So what it takes is a very similar radiative transfer equation to that one, where you account actually for the downwelling there. It's not the same, but it's very similar. Then in the next module, it can also do emissivity refinement. So it iteratively tries to narrow down what emissivity is expected. Then it calculates the so-called beta spectrum, which is basically just one equation in that specific module. And then it's the relation, the minimum maximum difference. That's what the MMD stands for. And RAP means ratio. So the minimum maximum difference is then related to what we measured in the lab. And here's what it looks like. We have in the on the y-axis, we have minimum laboratory measured emissivity per choice of samples. So what TESS does is you need a pre-filtered number of specific samples that you want to use, and then the minimum of that sample from your bands, obviously, is then related to the retrieved spectral contrast, which is minimum maximum difference from your measurement. So if you have 5 bands, 1 will be lowest, 1 will be highest. The difference between those values, that's your MMD, the spectral contrast. Understandable? Okay. So this is TESS. There's there are a lot of publications on TESS. I can also let you know a little bit more later, and I hope we can. It was more or less understandable. The second one in this group is direct test. Direct test is interesting one because it also kind of creates that relation. What it does is brute force matching. So there is a choice of spectral samples that they have. They create a simulation of all the possible states. So let's say we have grass at this temperature. What is the expected signal for the given sensor for this grass, for this temperature? And then we do it for many, many states. It's brute force, so it's slow. But it can have actually quite, it can be more accurate in some cases. So this is the equation, the radiative transfer equation, which is used. And the temperature is then derived by inverting the radiative transfer equation again. And then to match the database, they have a threshold, then try to narrow it down. Then obviously they have, as I mentioned, spectral library. They have groups in that spectral library, vegetation, water, and urban, altogether almost 4,000 cases. That's a lot of states that can be derived from that. So what they do is initial reduction of materials, which can be done using prior information. So if we have visible near-infrared or shortwave infrared bands, we can use the information from that to narrow down our huge number of samples to make it a little bit faster. And they use spectral angle mapper to narrow down the population. They have a very nice written paper, so if you're interested in direct tests, this is the source to look at. And the last algorithm, when everybody's done with taking photos. No, sorry. And the last algorithm that I'd like to describe is optimal estimation. Now, the implementation of optimal estimation for LST for the future ESA mission of LSTM was written by Mike. So if you have a detailed question on that, you can reach out to Mike here. This is what's going to be used in all the LSTM products in the future. So what optimal estimation does, I pasted here a quote from Wikipedia. It's it's an interpretation of probability of a state, where the probability is expressed by a degree of belief of an event. This degree of belief can be based on prior knowledge, and that's also crucial. So basically, when we have optimal estimation, we have a cost function, or we have iterative process again, where we try to simulate brightness temperatures top of atmosphere. So this algorithm uses top of atmosphere and includes the atmospheric states. And we use some a priori knowledge about the surface to narrow down what we're looking then at. And then the cost tells us if we're getting better or worse. And the lower the cost, obviously, then the better the guess. And so the algorithm then can increase the accuracy of the retrieval by simulating what the algorithm thinks is going to be the outcome versus what was the measurement. And the offset between simulated and observed is then used to train or to retrieve in the end. The prior knowledge can be that can be used in optimal estimation. For instance, the NDVI threshold method. That bases on the fact that urban materials have generally different emissivities to vegetation. So we can understand, we can partly expect highly vegetated surfaces to have rather flat spectrum. So this is already a first guess to be used. We can, other than NDVI, we can also use different methods. There is a classification scheme which is being developed for STM as well. And we can also make a first guess land surface temperature that can be taken, I don't know, from ERA 5 or from lookup tables. Basically, you can feed it whatever you wish to do. And the further away from truth, the higher the uncertainty will be. Now, the advantage of that specific algorithm is that it produces a fully traceable uncertainty budget. So you can understand all the components that Mike mentioned before a little bit better because they're described well in uncertainty matrices. Okay, so I've told you already about the different groups of algorithms, and I mentioned some of them. By all means, these are not all of them. There are many more. What I would like you to remember also is that algorithms base on different assumptions, and they will also have different inputs. So some of the algorithms, like for instance, the first two split window algorithms, will need total column water vapor as an input, which can be maybe taken from ERA 5. The University of Leicester algorithm needs fraction of vegetation, which can be maybe equivalent to NDVI. It also uses biome, which is land cover information, to narrow down the first guess, not the first guess, but the emissivity that is going to be assumed. If we look further, TESS and direct TESS take the downwelling radiance as input. So we need to have that information that's typically retrieved from some atmospheric models. So RTTOF can provide us that. And upwelling radiance, but I think in their implementation, they assume one equals to another. Then we have bottom of atmosphere radiance. TESS in this group, not only, but in this group, is the only one that takes pre-corrected data, bottom of atmosphere. The rest actually takes top of atmosphere brightness temperature. So you can express radiance in brightness temperature or watts per square meter, steradian, and micrometer. Then OE is the only one that actually takes first guess emissivity and skin temperature. So all of these are very different. Therefore, comparing them is not very easy. But we have conducted such an exercise. We have done that within the works for the LSTM future mission of ESA. And for that, well, Mike was also the main researcher. We prepared a simulation database containing all of these inputs, 20 years each month of the year, 1 day per month, pixels, as you can see here, input data was basing on ERA 5 and other sources, altogether almost 160,000 pixels. So this is just to compare the algorithms on a common basis. These are the variables which are the inputs for the algorithms. So you have seen that already in the table. While what we did with the algorithm intercomparison is we perturbed the values. We don't want to feed the algorithm the truth because the algorithm never will take the truth. You can't treat any input as truth because you don't know it. You know an estimation of the truth. So what we wanted to do here is to compare how well does the algorithm perform in the conditions which are slightly changed from the truth, and therefore we can understand the sensitivity of the algorithms to specific input variables. So we have both true variables, which we can treat as a reference, and then perturbed variables that are fed into the algorithms. And here are the results of the 5 algorithms I've presented upon, whereas bias means basically retrieved minus truth. And you see right away that there are different bias values for different algorithms. So this contains all the possible input perturbations. And the precision here is the standard deviation of the biases. So if I feed the algorithm more or less the same values, how different are the outcomes? If the changes from the truth are consistent, how consistent is the outcome? And so these are just plain numbers, and you could stop there, but that's very risky because the results of the intercomparison are dependent on many things. First one being basically conditions. So if we look first at the direct test here, you see very positive errors. It goes from positive +2 Kelvin to -2 Kelvin in all the cases here in these plots. You see very positive errors, very near to very negative errors. So this is the trouble with matching a huge database of presumed simulations. If we have a deviation from what is accounted for, then we have a big error. Then what's interesting as well is that the algorithms can go either both directions. For instance, URL algorithms are a good example of that. It can go negative, but it can also go positive, and you can see some patterns there already. Similar atmospheric conditions, similar temperatures at the ground will yield you different accuracies of the same algorithm. Then you see tests which is consistent to negative biases. I think there are very few values where the biases are positive somewhere around the desert areas. On the other hand, OE is consistently positive, and there is quite a low variation of that bias. So this is one thing to remember. The errors can differ geographically, different conditions. So I've looked at sort of spatial distribution of errors. Let's look at the temporal one. So this is the bias throughout the seasonality. So you see months, this is January, this is December, in each case. So what you'll see here is that there can be positive bias, for instance here, whereas in the winter months, or winter in the northern hemisphere, that's me being biased here, whereas we can have negative bias in the July, August months of the year. We can have that variation. So if you just average that will give you a very good average because it's near zero, right? But these are errors which can be hidden. Then if you have tests, you see there is a bias, there is a seasonality, but it's hidden. It's always negative to that direction. And then on the other hand, OE has a consistent bias, slightly positive, but it's consistent. And now the last thing I'd like you to remember from that is that they are also differently sensitive to land cover. So we divided all the biomes that come from the land cover CCI, ESAs, to groups, being cropland, sparse vegetation, urban, water, any tree that being forest, something related to forest, flooded vegetation, which is tricky because you can have water mixture with plants, and then bare soils and ice. And you can have very different results for those. For instance, if we take tests at bare soils, it will have rather a low bias, especially in comparison to direct tests, which is inconsistent and has a higher bias. But if we compare that to croplands or flooded vegetation, the bias is completely different. So the take-home messages here are that land surface temperature retrieval and land surface emissivity retrieval is an underdetermined problem. We have too few measurements because in each measurements we have at least two unknowns. There are various algorithms for land surface temperature and land surface emissivity retrieval. None of them is perfect. They will be sometimes better for specific applications. And TESS is advertised oftentimes for geologic applications, whereas it has its weaknesses in vegetation. all algorithms of that will behave slightly differently. They will have different inputs, and they have different accuracies. And on top of that, they are sensitive to different variables that I have presented you. They will differ temporally and spatially. So please take that into account and check what you're using. Yeah, and now I'm going to take some questions. Thank you much.
Hey, thank you for the interesting talk. I had a question when you actually I have two questions. When you showed the database where you compared something to a truth, I didn't really understand what you took as a truth.
As a truth?
Yeah.
So what we did is create a simulation database with all the true variables, and then we changed the values a little bit in each pixel slightly differently. So therefore, if you have true skin temperature, then for each pixel here, we create a slightly perturbed value of that. So if you have 300 Kelvin, then I don't know, it was randomly, or in some cases randomly within a given foreseen range. For instance, 300.1, 301, and so on. So each pixel is slightly different, so that you can then divide those perturbations, whereas, for instance, true minus perturbed will be in range of 1 to 2 Kelvin, or half Kelvin to 0 Kelvin, and then you can see how the algorithms perform within those different ranges.
Okay.
Does that answer?
Okay. I will look into it. I also had a different question. I think that several people said that the test algorithm was better compared to the split window, but when you showed this comparison, that you could see that the bias was higher for the test. So I was wondering, why that was.
Bear with me. Yes, that is correct. Everybody has their own truth. So depending on how do you want to compare them, you'll get different results. So what NASA does is they have validation sites. They use places like Lake Tahoe or and something in Namibia and on the desert. They will have a validation instrument there, and they will compare those measurements to what they see in their products. What we did was something completely different. We try to account for global conditions, different atmospheric conditions, and these are the results that we had. There are different opinions on how the algorithms perform, and in order to assess all of that, it's important to account for all the possible interactions of the radiative transfer equations. So if you have different atmospheric conditions, so I am obviously in favor of ours. So if you have different atmospheric conditions on a specific surface, this will be accounted for in our database. It will be less accounted for in Namibia, where the conditions are extremely stable. But obviously, all of those methods have their own right, have their reasoning. So I'm also not saying ours is perfect. It's a way to look at it.
I don't have a thermal background, and you and Mike have persuaded me to not go into this field. I mean, too much uncertainty. Too much uncertainty. So within the next 4 years, Prisma, SVG, and LSTM are going to be up there, but each one is going to use a different algorithm, right?
Yes.
So who is responsible for producing an interoperable product? Who is doing data harmonization? I mean, there is overlap in the bands, there is overlap in the spatial resolution, but apparently out of the box, you cannot use them interoperably, right? I mean, this is my understanding without being from this field.
It's not a bad understanding.
They are separate missions. They each have their own design teams. They each have their own algorithm selection. So they don't communicate. They do communicate.
Yes.
They have a common panel that sits together and works on harmonization. They are not launched yet, and they are constantly trying to work closer together. But it has to be within the confines of what each mission is doing. I can't promise you they're all going to come out with the same product. They're not all going to come out with the same exact. They should come out in a state that allows you to at least do some level of work between them together.
So, sorry.
Just to have a comment on that. Actually, I think LSTM, they are going to use the same tests, one of the test algorithms as well for consistency with, so they will be using optimal estimation as the core algorithm, the more accurate, but for the out of the box, I think they are still going to retain some element of the test algorithms.
I mean, for example, I work, with optical sensors. Sentinel-2 level 2A is for land, right? The atmospheric correction is not for marine science, oceanography. It's not made for that. So anyone who wants to use that needs to go a level back, a processing level back, and do the correction on their own. I mean, what I'm saying is, if its product is derived differently, then would it be some kind of functionality available for people to use different algorithms in Exchange to build their own interoperable products?
LSTCCI does a similar thing, right?
In theory, if everyone does their job right with uncertainty, you should be able to compare the algorithm results together within their uncertainty. So this algorithm plus or minus 0.5, this algorithm plus or minus 0.5, they give you for every single point you can compare it.
Well, yeah, but that depends. We have the same on sea surface temperature. There are multiple sensors measuring sea surface temperature, and John showed earlier on that you get different results depending on the sensor. But ultimately, there's only one sea surface temperature, there's only one land surface temperature. And part of the idea of working groups is that you actually then do these kind of comparisons to see what the different algorithms are telling you, because they are telling you something about the truth. And as Mike says, it's to do with the uncertainty in your measurement. And which is my question. There was another slide further on, which you showed a summary, again, another summary of different comparisons. Next one. That next one. That one. No, go back. That slide immediately caught my eye because it tells me there's something going on with I don't quite believe the optimal estimation because they're all saying the same. Why are they the same? Do you have a comment on that? Because if I see a number like that, the difference is all the same. Why would that be the case? Why don't you see the seasonality in the optimal estimation that you do in the others?
I can't answer that. Maybe Mike can.
Mike,
can you give Mike a mic?
So as far as we can tell, so that there is a tiny variation, not much as you can see, but as far as we can see, the reason why it's not getting the seasonal is because it doesn't seem to be explicitly absorbing the total column water vapor, and it's got more wiggle room on that. So one of the things that all the other algorithms had in common was the fact that they didn't really have a way of accounting for changes in the total column water vapor in terms of like wiggle room on it. So all of them had some sort of fixed dependency on it, whether it's banding and coefficients, or in the case of direct tests and tests, they were atmospherically corrected based on a value. There's not much you can do if that value is wrong in the coefficients. If that value is wrong, it can tip you over into a different coefficient band, whereas the OE was correcting on the fly each time for the total column water vapor. It could be an argument for testing more total column water vapor scenarios to see how far do you have to push it before you break the OE. because that kind of capability, eventually you just crank up the uncertainty to the point where it breaks. So we're definitely doing more tests to the structure of this, but fundamentally, it was the only algorithm that could dynamically account for incorrect total column water vapor as an input.
But the uncertainty will be different. So what we didn't plot here is the uncertainty level throughout seasonality, and that will
but the uncertainty changes by season, even if the bias wasn't affected.
And just to come back on the very first question, we are working very hard, we as algorithms teams, to account for all those difficult situations so that the users can use the products and not think about all those very complex situations. So that's our aim. More questions?
Thanks for speaking. My question is about the question in the very beginning, like you mentioned the mixed pixel problem. I was wondering if you can expand a little bit about this issue, like what kind of influence it will have, and are there any ways that we can use to reduce this kind of influence?
Yes. So what does it mean is basically each specific surface in a given pixel will have a slightly different temperature and a slightly different emissivity. So what we get over the whole pixel is an average. And so if your pixel consists, for instance, like that one, mainly of the parking lot, but partly of the cars, which are highly reflective, and then there's some vegetation, the majority of that will consist of the parking lot. So you can sort of make a weighted average to understand that better. However, obviously a sensor doesn't understand that. On that note, though, there are various algorithms that are trying to increase the spatial resolution of the thermal sensors using things like super resolution. And if they are well done, they will account for those differences and take the information for that from external sources. So, for instance, if you have a lot of those, I think all the future missions actually will have visible and near infrared bands which are higher, which have higher resolution than the thermal bands. So you can already use that and try to derive the super resolution product of that. And if you don't have that, you can still try to take, for instance, if you have an eco-stress product, you can take maybe Sentinel-2 from very near of your acquisition. You'll have no information about the temperature whatsoever there, but you'll have about the land cover, and maybe that can help you. And also Landsat has both bands in thermal as well as in visible.
Yeah, hi. I'm very interested in the emissivity of soils as I work with them. And my question is, TESS has like the huge advantage that you get emissivity per band of the emissivity per band. Does optimal estimation output the emissivity per band as well?
Yes.
And have you looked at how it performs in terms of like validation as well?
Yes, it absolutely does. So these two groups, mono window and split window, they assume emissivity, whereas retrieving will have every time emissivity per band. That gives you a spectrum.
Okay.
And with TESS, it's actually an interesting thing because due to your choice of spectral samples, you can actually tweak TESS to make it work better for you, for soils, for instance. And then if you have that, your vegetation accuracy will be horrible, but your soil accuracy might be much better.
Thanks.
Also, I want to say just how accurately the retrievals give you the temperature compared to the truth. I think there's been a lot of discussion about is this algorithm built on that one, but everything is within 2 degrees. Right? That's quite amazing. So my question is, what drives the need for the accuracy on measuring the surface temperature, and are you we need to have even more accuracy? And is it important given that truth itself is not that accurate, and it varies with time, and it varies with one thing next to another thing within a pixel and so on?
So the simple answer is application. There are various applications of thermal remote sensing. You will get an overview of that on Wednesday. But just to give you a simple example, for instance, vegetation health is a major thing which really needs accuracy. So basically, if a plant gets stressed, it will close stomata because it has too little water. It will at that moment stop photosynthesizing and its surface temperature will increase. And that is visible in the thermo-infrared. While it is not yet visible by the naked eye, it is not yet visible in the visible spectrum. And what it does, it allows farmers to water their plants in time, increase yield, water them enough and not too much, and therefore the more accurate the measurement, the better. So I think for the very, very accurate vegetation or agricultural production, we really need much more accurate surface temperature products. Some other applications are only interested in relative differences, where you have, for instance, I know maybe urban heat might be of interest there, because you can sort of compare different districts to one to another, and then plant more trees in one district, or use different surfaces for building and stuff like that. So then your 0.1 Kelvin accuracy is not that huge of importance. Whereas for some other applications, it's crucial. So depending on what you want to do, it derives the accuracy required.
Agricultural application get easier when you have much higher resolution.
It absolutely can, because it can then, if you have a field, basically, let me go back to that slide with what does the camera see? If you have a field which is smaller than a pixel, then you're not very much helped with coarse resolution. So you have like 1 kilometer pixel sizes, then it will maybe help you in, say, United States, maybe Argentina, where you have huge fields. Whereas if you have small fields, then it will not very much help you. And then again, the higher resolution usage is very strongly dependent on applications, because a lot of people tend to think, oh, I need much higher resolution to understand that, because they can't understand on that level what I'm showing here, what you can right away understand with your naked eye, what is what. Oftentimes you actually don't need it, but it really is crucial to understand your requirements from your application.
Thank you for your presentation. It's more of a thought from my side, not a question. What is the role of deep learning methods in this whole spectrum? Because at the end of the day, we are trying to measure something, and we know that there is also uncertainty associated to it. And as you rightly mentioned in the very first of your slides, that we know there are GraphCast models or ECMWF models which actually give us multiple forecasts in a day. And why would you not use these as an auxiliary data? And what could be, I mean, like, I'm so sure that you might have gone through the research of deep learning, and I would just like to know what is the role of deep learning methods in this exact problem statement.
So I'm a cautious person, and I would rather use machine learning for inputs. So machine learning is an amazing tool if you understand well what it does. And there are methods to retrieve temperature also with machine learning. I know they exist, but it's so much less understandable for us as humans. Where do they produce errors? And they typically go right if it's near to what the training data set was, and they're horribly wrong if it's far from that. And so the question is, can we trace uncertainty? We can't really. And can we treat them as reliable? Can we understand them well? So where I would see the role of machine learning is, for instance, as a pre-classification. If you want to treat a prior, give how much of that pixel is vegetation. I think machine learning will tell you perfectly. And then maybe it can also be used to derive additional information from it, like, is it very wet? Is it not? Things like that. But there are definitely other algorithms that are based on machine learning. So you can look into that. All the algorithms that I presented upon today are physics-based, though.
Yeah, so one follow-up question, like when you mentioned this University of Leicester algorithm, you also mentioned that there are 3 coefficients, and are these global coefficients or these are region and like these coefficients depends on the space and the time?
Yes. Okay. These coefficients are both dependent on space. That's your land cover here, biome, as well as temporal seasons. They will just create a huge lookup table that will look into the case by case. So we're looking into land cover, which is forest, and we're mid-latitude, northern hemisphere, winter, and we're looking under this viewing angle. That's what it's going to check.
Like as you told, like this is the operational algorithm for
Yes.
all Copernicus missions?
For Sentinel-3 SLSTR.
Yeah. What is the uncertainty of this, like plus or minus?
I can give you bias here from our simulation database. I don't remember from the top of my head, but there are continuous activities towards assessing the uncertainty, and I think Dave knows a lot about that. Yeah, I'm not going to try to answer that one.
Thanks. So I have a little question about the approximate, the Bayesian model. I think maybe it's a question for Mike. Can you get out of that approach the a posteriori distributions of all the variables, and then are you making any assumptions about them, the covariance structure, or they're unimodal? Because if you start doing the analysis and you have mixed pixels, the a posteriori distribution of the temperature might be 2 peaks, because you have 2 materials mixed into a particular huge pixel. So have you inspected the posteriori distributions that you get, and is there structure in them? Do they look funny or they look Gaussian?
They're not truly Gaussian now. There's a difference in the distribution, but we feed an input covariance that is not tied to one material. So it's tied to a range of materials. We have diagonal covariance is going in that tries to account for some variation. And a lot of the key power of it is linking those kinds of vary together in similar materials. So that helps the covariance. Also, we can try and increase the a priori observation covariance to include some of the correlated components as well. And that involves also from the other end. You can't separate subpixel materials. You just haven't been able to say this pixel is showing some of grass and concrete. The signal just doesn't come through like that as far as we've been able to tell. You could tell they're all mixed pixels. None of them look like a particular material with respect to line. We had a look a few years ago, but we gave it from that maybe we should be not been able to distinguish for this one is quality to both colors. We have not been able to do that.
So let me see if I understand. Everything that is fed into the this is like a Monte Carlo kind of thing, essentially, or okay. Okay. So, but everything that is fed is, I guess, is drawn from things that look Gaussian, I guess, ish. Okay. And so, is there any? What would you expect would any of the performance, which is excellent, I think is clearly the best, is the model that makes sense. So, would that break down with higher resolution data? Is there a scale dependence to the performance of this model? Do you have any intuition about that? Okay, cool. Okay.
Go to higher resolution, may be able to pick up more individual material, so you're likely to have an angular issue by, oh, now I'm looking at the side of the building. Whereas a localized just map the side of lots of buildings.
Okay, so that flatness and beautiful uniform color could break down and show up as a spatial biases as you go into high res. Okay, cool, thanks.
You said these are physics driven models, right? Do you, in any of the methods, do they put as input geolocation?
No.
I mean, for example, because it's interesting because you said, you could use machine learning output as input, and that unmixing is also an issue. And, we have clay embeddings, right? Clay foundation model trained on massive data sets, and they give you geolocation-based embeddings, which, again, in my very high-level overview, I could see them being used as input here, and you saw the global map with some bias in Africa.
Yes.
But if you fed that information in there, wouldn't that,
So we kind of can do. We don't use geolocation per se. The nearest to geolocation is biome, so that's the land cover type expected. Also because per given place in space, there can be a temporal change. So we're more interested in land cover as an input, but we can feed the algorithms some kind of a priori informations, all of them. In fact, we can tweak tests, make it a little bit more adjusted where we know already it's a vegetated area. We can create a MMD curve fitted to that vegetated area. So that's certainly possible. The more fitted you get for a specific location, the bigger errors you will have outside of that. So as I mentioned before, if you're interested in soils, you might want to tweak your algorithm to be perfect in soils, be lousy in ice or in vegetated areas, but for your application, it might be perfect. So yes, geolocation is not used per se, but it is indirectly used through land cover and all the other a priori parameters that you can use.
Yeah, I get what you're saying. I'm saying that you can fit the closest temporally Sentinel-2 to the clay foundation model, get a rich representation as a encoded geolocation.
Yeah.
Cool.
So just to be clear, the operational missions, they try to be universal. They have a focus, and you'll find out about that focus on Wednesday. But they still try to be as universal as possible. So they aim at maintaining some of the bias in order to reduce the bias everywhere. So